In this video, we are going to look at monotone sequences, bounded sequences, and bounded monotone sequences that converge. So first of all, monotone. To summarize what this definition is saying, basically, we want to determine if a sequence is increasing over its entire domain for all values of n. So for all values of n greater than n sub 0, if every successive term in the sequence is getting larger, then we say it's an increasing function. If every term in the function is decreasing, we say that it is a decreasing function. In other words, an increasing function is something that's always going up, 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 up. It never turns around and goes back down again, okay? A decreasing function is something that always goes down. It never goes back up again. So a monotone sequence is simply either a sequence that is always increasing or always decreasing. It covers both of those. We say it's monotone. Some textbooks will call it monotonic. So the first thing we want to do is look at two examples graphically. Okay, so if we were to graph this sequence as though it was a function, graph f of x equals 2 plus 3x, we can see that's a linear equation. And so it has a y-intercept of 2 and a slope of 3. And so we know that that linear equation is always going to be going upward. It's always increasing. So the function is increasing for all values of n greater than n sub 0. Therefore, it's an increasing function, and it is monotone. In our second example, you could graph this as 1 over x. And so 1 over x for n is greater than n sub 0 is always decreasing. So again, as a function, we're ignoring the values of x that would be negative because as a sequence, we don't have any negative n values. N is always going to be positive integers. So this is decreasing everywhere, so it is decreasing monotone. Well, we also want to be able to determine algebraically if something is monotone, if it's always increasing or decreasing. So in the next three examples, I'm going to show you how to do that. So for the first one, I want to show you that the function is increasing for all values of n greater than n sub 0. So the way that we do that is we say, okay, well, we want to show that a sub n is less than or equal to a sub n plus 1. In other words, each term is going to be less than or equal to the next term. If every term is smaller than the next term, that means every next term is getting larger and larger and larger, and therefore it is increasing. And so what we do, we say, okay, well, here's my sequence, a sub n. What would a sub n plus 1 be? So we simply take out the n and we put in n plus 1. And so that's what I did there. Every place there was an n, I substituted in an n plus 1. And so now we want to show that a sub n is less than or equal to a sub n plus 1. So I set that up right here. Okay, simplified it a little bit. All right, cross-multiply to get this. So in other words, you're multiplying the numerators by the other denominators. And so now multiplying the left-hand side to get this, multiplying the right-hand side to get that. Now the 3n squareds cancel out, the 9n's cancel out, so all I end up with is 0 is less than or equal to 6. Well, that is always true. That's an identity. That is always true. So in other words, this relationship right here is always true for all values of n greater than n sub 0. And so therefore, since it's always true, it's always increasing. So we've showed that it's always going to be increasing. In other words, for all values of n, the n sub 1 term is always going to be larger than the a sub n term. Next example, same logic. So we have 3/4 to the n power. So what we want to do is we want to show that a sub, now we want to show that it's decreasing. That means every successive term has to be less than or equal to, okay, less than or equal to for all n. And so what I did here was I simply divided both sides of this equation by a sub n to get this. Okay, so you take both sides of this, divide it by a sub n plus 1, divided by a sub n plus 1, and you would get this. And then from there, here's my a sub n divided by a sub n plus 1. Well, 3/4 to the n plus 1 could be rewritten algebraically as 3/4 to the n times 3/4. These cancel out. You're just left with 1 over 3/4, which is 4/3. Okay, well, 4/3, remember, we're taking this and it's greater than or equal to 1. 4/3 is always greater than or equal to 1 for all n. And since this is an identity, it is always true. It is decreasing and monotone. Now, the last example here, I didn't tell you to show whether it's increasing or decreasing. We got to figure that part out. All right, so let's create an a sub n plus 1. Now, I put a question mark here because I don't know if it should be a less than or a greater than symbol. So I take my a sub n plus 1, when we simplified this over here, we get 1 over 5n plus 5n plus 5 plus 2, which is 5n plus 7. That's what we got here. And then cross multiplying, we end up with this. And then you can cancel out the 5n's. Well, 7 is greater than or equal to 2 always. All right? So this is when I know which way to put the inequality sign. Here I didn't know which way to put the inequality. Here I didn't know, but here I do know. 7 is greater than or equal to 2 always. So therefore, since the left-hand side, a sub n, is always greater than the right-hand side, that means it is decreasing everywhere and therefore monotone. Is a decreasing monotone sequence. All right, so that's how you can determine if something is monotone algebraically or graphically. The next part is being bounded. So to kind of explain what this is saying, we need to determine if there is an upper bound or a lower bound to the sequence. In other words, is there a value that the sequence will never be less than? Is there a value that the sequence will never be greater than? If there's a sequence that number will never go below, then it's bounded below. Okay? It has a lowest possible value. If it has a highest possible value, it's bounded above. All right? So let's say you had a sequence that went between these two numbers. They're like horizontal asymptotes. This would be bounded below by this, whatever this is, bounded above by this. So it's bounded. If you have something, could have a lower bound like exponential function, but an exponential function doesn't have an upper bound. It goes up infinitely far. That is not bounded above. So some functions are bounded, some are not bounded. If a function is bounded above and below, then we say it is a bounded sequence. It has to be bounded above and below. It is bounded sequence. And the reason that we want to know that is because of these two theorems right here. The monotone convergence theorem says, basically, if a function is monotone and it's bounded, then it's convergent. Convergent sequences are bounded. And so basically what we have to show is that if something is monotone, always increasing or always decreasing, and it's bounded, then it is convergent. So let's take a look at a few examples. So the bounded part, you kind of have to do intuitively. The smallest value of n here is going to be n equals 1, because we start at a sub 1. And so it's going to be bounded by 1 on one side, okay? And the largest value of n, as n approaches infinity, then this whole thing approaches 0, all right? So when n is 1, and that's the smallest value of n, we have a 1. When n is going towards infinity, then this whole thing, the limit of this, is approaching 0. So it's never going to be greater than 1. It's never going to be less than 0. So it's bounded above and below by those two numbers. So it's bounded. Think about that for a little bit. Then we can show that it is monotone using the techniques I just showed you. We take a sub n question mark, a sub n plus 1, and multiplying these out, algebraically cross-multiplying. These cancel out. So 2n plus 1 is, this we can show that this is always going to be greater because these cancel out here. So 2n plus 1 is always going to be greater than 0 for all n. So therefore it is monotone. And since it's bounded and monotone, it is convergent. The next one is the sine function. Well, we know right off the bat that that's not monotone. We know that the sine function goes up and down and up and down and up and down. So there's really not much work to do here. We know that the sine function is bounded by 1 and negative 1. Okay, sine function is never greater than 1. It's never less than negative 1. So it's bounded, but it's not monotone, and therefore it's not convergent. And the third one. And this one is supposed to be for, I believe, n is greater than or equal to 2. When n is equal to 2, we get 3 squared over 2. Remember what a factorial is. You're going to see factorials. I don't remember if I explained this to you, but like n factorial, like 2 factorial, simply means 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So there's some good videos out there that will explain factorials. So this becomes 9 over 2. So the smallest that n can be is 1, or 2, I'm sorry, for 2. And so it's bounded by 9 halves. And then as n gets infinitely large, a factorial would get larger faster than an exponential. Factorials get larger faster than exponentials. So therefore, since the denominator is getting infinitely large faster than the numerator, this whole thing is going to approach 0. And so it's bounded by 0 and by 9 halves. And so since 9 halves is larger than 0, 9 halves would be the above bound or upper bound. 0 would be the lower bound. Now, here's where we do the monotone thing. And we see that it is monotone. And so since it is bounded, since it is monotone, it is convergent. So I'll let you go through the process here. Again, we don't know if it's greater than or less than until we get to the final steps. And so, one other thing I guess I probably should explain is this. If I have some room somewhere, let me do that. So we can write n plus 1 factorial as n plus 1 times n factorial. The reason for that is n plus 1 factorial. I think that's what we had here. Yeah. Oh, I'm sorry. N plus 1 times... So n plus 1 factorial. So let's just say we had 5 factorial. We can write that as 5 times 4 factorial. Right? So if n plus 1 is 5, then n is equal to 4. And so n plus 1 factorial is 5 factorial. And so n plus 1 is 5 times n would be 4 factorial. Now, why is that true? Well, if you understand that 5 factorial is 5 times 4 times 3 times 2 times 1, then we can write this as 5 times 4 times 3 times 2 times 1, which is 4 factorial. So that's a little tricky stuff, and you're going to see this happening again in this chapter. So make sure that you understand what happened here. All right, take a look at that, kind of go reason through it out, but you need to understand the concept of factorials, of course. So that was a little bit of that nifty stuff that went on in here. Changed n plus 1 factorial to n factorial times n plus 1. All right, now just a few random problems to finish up this long section. So we just want to find if these sequences converge or diverge. So I took the limit, right? So the limit of this particular sequence, first of all, I divided everything through by n squared to get this, right? And so that gives me this. And so now this goes to 0, this goes to 0. So we end up with the square root of 4, which is 2. And so the limit of 2 is 2. And so it converges to 2. Remember, if there is a limit, if the limit is some value L, then it converges to that limit. In the next one, I rewrote it so that it was a fraction. In other words, taking e to the negative n and making it 1 over e to the n. And so I got this. Now I can use L'Hopital's rule. When we want to find the limit of a fraction like this, then we can take the derivative of the numerator, the derivative of the denominator. That's L'Hopital's rule. And so then I did it again. Took the limit again, took the limit again, took the derivative again, took the derivative again. Remember, you can apply L'Hopital's rule as many times as you want. So the reason why I did it again is you could determine what the limit is here, but it's easier to determine what the limit is here. A lot of times, to do something like this, you have to know, is the numerator getting larger faster than the denominator, or is the denominator getting larger faster than the numerator? Well, the numerator is linear. The denominator is exponential. Exponentials get larger faster than linears. So the denominator here is getting larger faster than the numerator, so this whole thing is approaching 0. But that's much easier to see here, because the numerator is staying constant as the numerator is getting infinitely large. The whole thing is approaching 0, as I demonstrated earlier. And finally, in this last problem, I didn't really show any work. So first of all, it is not bounded. And the reason it is not bounded, if we let n be equal to 1, then we get n factorial, 1 factorial, over 2 to the 1 is 1/2. So that's a bound. It's bounded by 1/2. But what happens is n gets infinitely large. Well, remember what I just said. A factorial gets larger faster than an exponential. So as n gets larger and larger and larger, the numerator is getting larger faster than the denominator. So when the numerator gets larger faster than the denominator, it approaches infinity. So there's no upper bound. You got a lower bound, but you don't have an upper bound. So it is not bounded, and therefore it is not convergent. And that is it for this video, and that is it for this first section in sequences and series. The first 2 sections are pretty long. There's a lot of information in these 2 sections, this one and the next one on infinite series. And then the next 3 or 4 sections after that are a little bit shorter. We're just going to be applying some tests, and they're going to go a lot easier. But make sure that you watch these videos a few times. Go find some other videos, do the homework, and make sure that you absorb all of the concepts that we've gone over here. All right, have a good day.